So today I want to start with this quote that is also in one of your readings from Carja in 1903, so a long time ago. And his quote says, if we knew exactly the laws of nature and the situation of the universe at the initial moment, we could predict exactly the situation of that same universe at a succeeding moment. But even if it were the case that the natural laws had no longer any secret for us, we could still only know the initial solution approximately. If that enabled us to predict the succeeding situation with the same approximation, that is all we require, and we should say that the phenomenon had been predicted, that is governed by laws. But it is not always so. It may happen that differences in the initial conditions produce very great ones in the final phenomena. A small error in the former will produce an enormous error in the latter. Prediction becomes impossible, and we have the fortuitous phenomenon. So last time at the end, we saw one example where using the logistic map and starting from different initial conditions, it was quite impossible to predict the behavior of the system after a certain number of generations. And today we're going to talk a little bit more about these types of systems that we call chaotic systems, which display a number of very interesting characteristics. They are aperiodic. They exhibit these very sensitive initial conditions. They are governed by one or more control parameters, which can cause the chaos to appear or to disappear. As we saw in the logistic map, we had that growth parameter that played a very significant part in the dynamics. So, and we use the logistic map because it actually serves as a very good prototype. It is one of the simplest chaotical systems that we know of because it's one-dimensional and it has only one governing parameter. And however, it exhibits such complicated and interesting dynamics that, that we see in other systems that seemingly look much more complicated. So just to recap a little bit more, last time we looked, we saw that some very interesting chaotic behaviors can appear in one-dimensional, and then we didn't talk about two-dimensional maps. So discrete systems, and we talked about why that happens particularly in discrete systems and what the differences are between discrete and continuous systems. Now, in terms of continuous systems, we went over and discussed the different types of flows and equilibria that can appear for one and two-dimensional systems, and we saw that for linear or even for nonlinear systems, and we talked about how we can linearize the nonlinear systems using the Jacobian matrix. It is very easy to use the type of phase portraits that we saw and to use the type of flows that we talked about, such that for every initial condition that you give me, I can follow the flows in space and tell you where the system will be at a certain time in the future. However, what happens for larger dimensions? So behaviors are quite predictable for one and two dimensions for the continuous case. And in the continuous case, it is necessary to have a three-dimensional nonlinear system for these weird types of behavior to appear that we call chaos. So, and necessary and sufficient is actually to have a map that is non-integrable. And we won't go much into that, but I wanted to mention to you, so we are not able to solve that function in closed form, basically, that's what it means. So today we'll talk about continuous time system in 3 dimensions that exhibits these phenomena of strange attractor and chaotic dynamics, and it is a very famous system called the Lorenz system, and you guys probably already heard about it or studied it, but we wanted to go over it because it's one of the most studied systems, and it's actually, the dynamics are quite beautiful. So I think that's another reason why a lot of people just go to the Lorenz system, because it's so visually beautiful too. Lorenz, I think in the 1960s, attempted to study convection rolls in the atmosphere. And so as the rising air cools and as the colder air, so the falling air warms, there are these churning flows that are established, and he attempted to model them mathematically using nonlinear systems and to try to predict their dynamics over time. And he used these nonlinear models, and he used these very antique computers that he had, where he could get, he could get sort of like the numbers over a certain number of iterations of his map. And what he noticed is that if he started with a little bit of a different initial condition, he noticed significant departure from his initial runs of the simulations, and that was one of the first time that people have noticed this. And if I'll post on the website his initial paper, which is really easy to read, and I encourage you guys to just try and read it. But I wanted to write first. Let's write the equations that he had. So these are the equations that are called the Lorenz system, that he used to model these flows in the atmosphere. So just looking at them, can you guys notice anything about these equations? Like what are things that you've noticed about them? Are they linear? Are they nonlinear? Can you tell any straight up any like stability points?
Those are all Z's, right? Take the cross there.
Yes, this is Z. Sorry.
This is Z as well?
That's Z.
Should clear the other way, but.
So here the parameters, you have these three fixed parameters. Sigma r be larger than 0, and your variables are x, y, and z. So is this linear or a nonlinear system? And where do the nonlinearities come from if it's nonlinear? And how many nonlinearities does it have? Do you want to try?
Not really.
How can we tell if it's linear or nonlinear?
Well, maybe, why doesn't everybody sort of talk to somebody next to them and everybody figure out if it's linear, nonlinear, and what the nonlinearities are?
Could you lower that?
This? Yeah.
Oh, okay, that's all.
But I can't.
I mean, it's every day for us.
Just one. So that's a good comments in here.
So I just wanted to point out really quick, this is very valuable information right here, which are the fixed parameters and which are our variables, right? We're always interested in the variables when we talk about linearity and nonlinearity. So does someone want to tell me whether the system is linear or nonlinear?
Well, now we should be able to go around the room and just ask anybody randomly, right?
Right.
So what about you guys over there?
Okay.
Linear, nonlinear?
Well, I'm kind of going out of work here and I haven't taken calculus in a while, but we decided that they could be linear because I don't know, it's like 50-50, right? Because if you integrate x with respect to something other than x, like t, then you don't end up with the problem of having a derivative on one side and a variable on the other. So then it should work. But
so which are our variables here though?
X, Y, and Z.
X, Y, and Z. So
hang on a second. You said if you take the time derivative, you don't end up with that problem. Are there already time derivatives in here?
I guess what we were.
So just remember that these dots mean time derivatives.
Okay.
So it's a conventional thing. We mentioned it once before, but it's not that intuitive.
Wait,
Is that what he said?
Okay. Well, I tried. Somebody else's tried.
does anyone have another opinion? Or should we just flip a coin?
Everybody has opinions.
Yeah.
We had the hypothesis that that linearity meant that the terms in the equation were of the same degree, and that you calculate that degree based on the number of times a variable appeared in the term. And given that there were equations with terms that have degree of higher than 1, it was
Like what?
Like the second one.
Like
y dot, like xz. X,
and
y.
this one maybe? Yeah, so that's exactly it. So it's very important to know there are a lot of different symbols appearing here, right? Like you have all these different parameters, you have all these different variables. Parameters are constants. If you have trouble with them, always just put 1 instead of the parameters in your mind, and just like, it's sort of like getting rid of them. So if you look at the first equation, if we put 1 instead of here, we just get this. This is a linear equation because it only has the variables that we're interested in only appear at a first power, and there are no functions of the variables. So we talked about how nonlinearity means any product of the variables with themselves or with other variables or other functions, more complicated, so nonlinear functions of the variables were a nonlinear map. So a linear map means basically f of ax plus by equals a f of x plus b f of y. That's a linear map. So anything that doesn't satisfy this equation will be nonlinear. So anything that appears of this type will make it a nonlinear equation. So if I have something like this, this is a linear system. Now, where y, the derivative in y is 0. Now, if my derivative in y now is x minus y minus xz, and z is 0, let's say, already I see terms that appear as products of these variables, right? So I see terms of this form. So this makes the system nonlinear. And again, the same thing with this term. So always ignore the parameters. It's as if the parameters don't exist for now. It's as we saw in the logistic map, it's the parameters who introduce all these like interesting bifurcations in the system. But if we just want to determine linearity or nonlinearity, always look at the variables. Are there products? Are there functions of them, like costs, cosine or sine, and stuff like that? Is that more clear? Okay. So this system, how many nonlinearities does it have? 2. What can we say about the point 0, 0, 0? If you start there, where do you go? So when I say if we start there, just look, if we put x, y, z equals 0 in these equations, what do we get?
Oh, you stay there.
You stay there because then all the velocity sort of are 0 too. So if you start at 0, you stay there. So the origin, one of the things that we notice about the system, it has these 2 nonlinearities. Origin is a fixed point. What happens now if you replace, let's say you replace x with minus x and y with minus y? we get? So if, let's say, minus, so if A, B, C is a solution, what can I say about minus A, minus B, and C? Is that also a solution? And how do we test that? We test that because let's replace x with minus x. You get minus y minus plus x, right, equals, minus just goes in front of the derivative. So then if I multiply by minus 1, you get the same system as before. So we call this system where if x, y, z is a solution, it also implies minus x, minus y, and z a solution, a type of symmetrical system. It's not entirely symmetrical because I can't replace z with minus z, but it has some symmetry to it that I wanted to point out to you guys.
Would you modify that and say symmetric in x versus y or something?
In x and y, yeah, in these two dimensions. So if
So what is that? Can you tell us what that means, like intuitively, the symmetry?
Can I ask a question? Why can't you replace z minus z?
well, if we replace z with minus z here, what would you get? So if I would have x, y, z,
So you wouldn't get the symmetric minus z.
would you get the same equations? That's my question.
You would get xy plus b.
So you would get minus here equals minus x minus y. So this would be xy plus bz, right? So then it would be minus xy plus bz.
Which is
So this
not-
would be not the initial equation that you have.
Is there any way to know like which dimensions it's symmetrical in, or do you just have to try them?
I think generally it's visible by eye sometimes, but usually you just have to try. Because for example here it's not, I mean, you can do a quick calculation in your head that z is not symmetrical, but I don't want to spend too much time here. I just wanted to point out, so generally if we have a sort of seemingly complicated system like this of 3-dimension, it's good to first, take your time and look at it and see, okay, so what can I say about it? Is it linear? Is it nonlinear? How many nonlinearities does it have? Is there any fixed point that just jumps at me? And so on. So it can be proven that the origin, if we want to study the fixed points and the behavior of the system, the origin is a fixed point for the system for all values of the parameters. Now, we won't do the math in class, but it can also be proven that if r larger than 1, there are a pair of these symmetric types of fixed points. So x, y equals either plus or minus, and we saw that from the symmetry. These are also fixed points for the system.
So this is an x or y can equal plus or minus for the p times r minus 1?
Yeah,
X and y, x or y? Is it x here?
x equals, so
X equals y equals.
yeah.
Do you get that by just putting in 0 for the rates of change?
So you can solve it. So if so you can test, for example, that this is this is a solution for the system.
How did you derive the solution from the system?
If I'm happy to talk about more about that, but I don't really want to get into the exact.
Well, what does it mean to be a fixed point, I guess? Like in principle, how could you go from there to there? I think is what you're asking, right?
Just read it briefly. You don't need to look it up.
So for example, if you put these to be 0.
Okay.
Yeah, so if you start there, you stay there.
So fixed points are always solutions where all the time derivatives are equal to 0.
And now, so these are all different types of fixed points. Now, if we look at their stability, in a similar way that we looked at last time, we can see that there's this interesting phenomenon going on that for R under a certain threshold, which can be explicitly derived, these two types of fixed points are linearly stable. So if you start near the fixed points, or if you start in a certain vicinity of the space, you go to the fixed point. And I actually will show you a little demonstration in just a few minutes. However, if R is larger than this R age, then you have a complicated behavior arises. And the particular case that Lorenz looked at was sigma equal 10, B equals 8/3, and R equals 28. So these are the values of the parameters that he studied and that people keep looking at when they talk about the Lorenz system. And we're gonna just look. I'm gonna use the computer for that. So maybe you guys can move to the other side, and we're gonna look and see how the system behaves for these different values of parameters, because that's the easiest way to visualize these things.
Oana, for 3, you wrote that when R is in between these two values, you get this. What is that equal to, that term?
Yeah, sorry.
This plus or minus sigma, this whole thing.
This is this critical value RH.
Oh, that's the critical. Okay.
Yeah. RH is this critical value. For R smaller, it's kind of like, it's the same type of sort of bifurcation point that we saw in the logistic map last time.
Hold down the on. There we go.
So let's look at an example where this parameter R, which is A here, is just a different notation, is under that threshold value. So let's say you start the system, and this is sort of what the system behaves when it starts near, behaves like when it starts near the fixed point. So this is one of those two. The two fixed points plus or minus 1, and we start near it, and you go to it.
What's plotted on the y-axis?
On y-axis, I think it's Z is plotted. Now, let's look at what happens if now you start with R above that threshold. So this is with an R above the RH threshold. I'm going to speed it up a little bit. So if we look at what happens to the trajectory, instead of spirals, let's say, to the right, and it stays there, and it does these orbits for a little bit of time, and then it spirals back to the left, and then again it does the orbits, it spirals back to the right. So it can actually, it's not visible here, but if you start, it's very hard to predict how many times it circles inside here before it spirals back. And so it creates the surface where if you start with a different initial condition, and we're going to show that in a minute, the trajectory that you get can be quite different. So this type of sort of trajectory that you see here, you guys, we're gonna go to the paper too and talk a little bit about that. But this is what is called a strange attractor. It's this surface where all the trajectories will eventually go into the surface, so they're close enough together, yet they can be very far apart from each other when starting from different initial conditions.
Do they ever overlap?
In what sense overlap?
Like, it's hard to tell, but maybe some of these lines just follow the same path they had followed previously.
So these paths are very dense in the surface, but I'm not sure. It's possible that I don't think they ever, but it's sort of, the theory is that the surface is sort of dense in these types of trajectories.
If it's deterministic and they overlap, then there will be periodicity, right? And if there's periodicity, it wouldn't be chaotic.
That's right.
That's true. Yeah,
so
good point. They never overlap.
And they can never cross either.
And they never cross. So we're gonna see. I'm gonna stop this one for now, and we're gonna look at it in three-dimensional space now. So this is the sort of the type of trajectory that we saw last time. This is now in three-dimensional space. So it. How about a web search for it? So they may seem like these trajectories are crossing. So it's very easy to assume that here they actually cross, but they don't cross, because if you look at it in three-dimensional space, you see that they never really cross each other. It's only the appearance that they cross. So this is plotting x and z, and you can play around and do looking at x and phase-space dynamics x and y and so on. So plotting two of these variables. This is if we plot in two dimensions. Basically, we plot x versus y, x versus z. So you see, again, this type of dynamics that appear over time. Now, we can also look and see what happens with x just as a function of t, right? This is x over time. So time is on the x-axis, and the variable x is on the y-axis. I'm going to speed it up a little bit. And again, you can see this type of sort of complicated dynamics where the system is not periodic, and it crosses over in positive and negative direction, but never really settles in either to a fixed point or to a cycle or to anything that you can really predict.
Now, can you have that type of non-periodic, etc. behavior while still having it not chaotic? So that if you start with an initial position faintly different, it still has the same, hones in on the same behavior after a while.
So we're going to now we're talking about this chaotic behavior as something very abstract, right? We're going to, later on, a little bit, in a few minutes, I'm going to give an exact definition of what chaotic means. And so we're going to talk about chaotic.
Again.
Yeah.
Okay, fine.
So here I wanted to show you guys sensitivity to initial conditions. So for example, we start, actually, does someone else want to do this? Click on a button.
Good.
Okay, so click on any point here in this space, and then try to click again very close to that point, or anywhere, like we're trying to exhibit the sensitivity to initial conditions, so close to that point or far away from that point, wherever you want. Okay, so now already we see that they diverged. And they'll, what is interesting is that they're going to keep fairly close to each other. So they're all keeping close on this sort of surface, which we call a strange attractor. However, at any time point, they could be very far away from each other. And in that sort of sense, we say that in these systems, prediction is impossible because these small uncertainties are amplified very fast, and we're actually going to quantify how fast they're being amplified. We're going to make that a little bit more precise. Does anyone else want to do it? Do you want to start with different initial conditions and see?
See who can put the dots close enough together that they don't diverge.
Extra credit.
Extra credit, yeah.
So basically, you just clicked right on top.
Yeah.
I'm a winner.
Oh, there's some sort of,
Oh.
let's wait for it. We did it all day.
Okay, now they're
Whoa.
they're quite, yeah, no, they're quite off.
Completely.
That was quite a long,
Dependence to initial
yeah, that was very good. Awesome. So we're going to quantify that a little bit more. What does this sensitivity to initial conditions means? And it's basically given by, and I'm not going to go very much into the details. Whatever I tell you about in class, we don't have enough time to go into the details, but you can always go and search all these things that we talk about in more detail if you're interested. So what I wanted to tell you guys about, maybe, because I'm going to use the computer fairly soon again. Can I write over there just for a little bit? Oh, thank you. So we're going to, something to quantify this behavior is what's called the Lyapunov exponent.
If you want to sit here, you can
Yeah,
close that chair.
Well, this is fine.
So
Go to sleep.
basically, the Lyapunov exponent is trying to, at every time point, measure how far the two trajectories diverged if you start, so this is sort of the divergence over time, if you start with divergence delta 0. And what can be computed is that delta t is approximately equal to delta at time 0 e lambda of t, where lambda is called the Lyapunov exponent. So as we see the divergence here, if lambda is positive, is greater than 1. Sorry, if lambda is positive, this diverges exponentially. If lambda is positive, this function goes to infinity, right? So that's why we say that this has, the divergence has an exponential growth.
That's exactly what we just saw, right? So the exponential growth, because things are, think about like 2 to the first power, 2 squared, 2 cubed, 2 to the fourth, that's exponential growth, right? And so very rapidly, you can go from almost no difference to a huge difference. That's exactly what we saw.
But the two you got, the difference between the 2 points were limited, as far as I could tell. There were 2 strange attractors, right?
There was one strange attractor.
One or?
The whole surface.
Okay, there's one strange attractor. I didn't see any movement outside of those 2 circular places. Would I have seen it if I waited long enough?
No, so the movement always stays on this strange attractor.
So
but the trajectories, if you start with a trajectory that's like very close to each other, when we say that they diverge exponentially, So the divergence here, this sort of this initial difference grows over time exponentially.
So his question is, if it grew exponentially forever, wouldn't they end up infinitely far apart from each other? And then wouldn't they not be on this strange attractor?
Not.
Isn't that what you mean by the difference between the two is grows exponentially? That
Well,
they get further and further apart?
I think this is only true for a certain amount of time.
Yeah, so eventually, I mean, you always stay on the surface. The exponential growth is what is possible to have, but eventually it should dampen out. So if you look at, I think in
They
the,
grow until they don't.
so if you look in the book, in the chapter that I put online, they show this graph of, I think it's called, this is with time, and this slope. So this is over time, like as we see the Lyapunov exponent is computed as the difference as a function of time. So over time, it's sort of, it's actually, it varies around this sort of straight line, and which with the slope lambda. And you know, it's once after some time you actually don't have here. So after some time it can grow up to a certain point. So it's explained more in the book. But on that surface, like don't think that just because it's a surface. So what I wanted to make clear is that, you know, you stay, it's a certain way that there's order in the sense that you're sufficiently close together on the surface. You always stay on the surface, and if you let the trajectories, like evolve over time sufficiently, that surface will be very dense, and we're going to talk about sort of like its fractal sort of type of properties next time. But at the same time, if you start with two initial conditions that are extremely close together, that difference between them can exponentially grow with this type of given by this type of constant number. And every mapping, so for example, for the Lorenz system, here lambda equals 0.9. So this is sort of the type, this is the number characteristic to the Lorenz system. But every system has a different number on these surfaces, where this sort of, it's a way to quantify how fast you can diverge from another initial condition.
So can you think of the surface as kind of like all the different possible states? So if we're thinking of like a weather system, right, and the like attractor space is kind of all the different possible atmospheric conditions. And so if you start something with two worlds with very similar initial conditions, they're going to diverge, and eventually over time, you know, sometimes you may have the two states kind of come together so that the worlds kind of look like each other, but that doesn't mean you're actually predicting them, because to get there they took different paths. Would you say that's right?
No, that's definitely right. And sometimes, and maybe we didn't see it in these examples, but you know, after it's possible for those curves, even if you start like one goes this way, one goes that way, but like eventually they could end up very close together again. And once they're close together again, again, we cannot say that they're going to remain close together. The divergence again will be sort of, it will grow exponentially, but that doesn't mean that they cannot come back together again.
Does this occur in orbital shells in atoms with electrons?
I don't know.
Okay.
You know, about your comment, I don't think the attractor would be all the possible states. That's the axis, that's the state space. The attractor is actually what the relationships between all those different variables define as possible, as opposed to
Like it wouldn't be possible to have a tornado on every square centimeter of the world at one time. So that's not going to be on the surface. It's going to be in the space.
Right, yeah. The space is like, exactly, the space is like really anything. The attractor is what can actually happen given the relationships that you set up.
So as far as electron possibilities, basically.
Electron orbitals are can only talk about probability distributions, you can't talk about paths. So the answer is yes and no.
Can we talk about some of the applications of this? Like, where
We're
would something
gonna-
like this?
Right. So I think in the paper that we had to read, we're going to mention some of these. And this is basically, so if we wanted, let me see what I have before we move on to the paper and to some of the examples that we had.
Can I say one other thing? I think
Yeah.
that'll help answer this question. So this exponential growth, obviously it can't go on forever. It goes on for about 1 over lambda. That's about the time scale that you can expect it to be accurate for. Once it gets to above 1 over lambda, things might change. But
1 over lambda what?
time.
So are we saying that the system does not have a constant exponent? Exponent changes?
I think that it has an exponential growth for time 1 over lambda, right? Or something of order 1 times 1 over lambda.
This is related to his question about do we need
Because eventually the two paths have to
There's not limit.
come back together. There's an upper limit on the delta of t. And so you can just rearrange that equation and say if delta of t gets to the maximum limit, that, like, so you can call that like delta max. You can just rearrange the equation and solve for t, and you see that it depends slightly on what you start your initial delta is, but it only depends logarithmically on that. So to a good approximation, this will be true for about a time of 1 over lambda, and above that, things might change. But that still could be a very long time.
And that doesn't mean that after the 1 over lambda, you can suddenly start predicting the system again.
Right.
Right? It's you're limited by the size of the system.
Yeah, you never can predict the system, and the things always, the paths are always getting farther and farther away from each other in a sense that the whole path, like all the curves together look completely different. But the actual distance that any 2 points are apart from each other can't grow without limit. But it does grow exponentially for short times when the 2 points start close enough together. And that's really important.
So are you saying that it's in the strange attractor only until timescale 1 over lambda, or?
No, I'm saying, sorry, so that might be unclear. So it's always in the strange attractor,
Mm-hmm.
but when it's, like if it's doing some sort of weird thing like this, and like this thing, the maximum, we were plotting on x versus z. So if you're looking at the maximum delta z, we could write this equation for delta. So for each dimension, you have one of these Lyapunov exponents in one of these equations. And the maximum difference in the z's is this distance here. That's delta z max. So it can never get bigger than that, because otherwise it would be outside the strange attractor. But all I'm saying is that for a time less than something like 1 over lambda, this is exactly true. That's all I'm saying. And this is still very different than non-kinetic behavior. Non-kinetic behavior, this thing doesn't grow. This sort of delta z of t is just related to delta z of 0, and it's not growing exponentially at all.
Yes, wait. Yes, it is.
You can also have systems that grow exponentially that are not chaotic. They're unstable.
Yeah, okay.
Yeah.
I mean, if I took 2 ping pong balls and throw them with somewhat different initial conditions, they will tend to diverge.
Not exponentially.
Not exponentially, linearly with respect to time.
Yeah, that's the important part. It's in
not
short.
so that's not that e goes to 1, the e term. It's e becomes t instead.
Okay, yeah. It's growing less. It's growing slower than
linearly.
exponential. Not necessarily linear. It could be quadratic or something, but
Because of the surface
depending
they're going across.
depending on what
yes.
you're doing. But it's not exponential. It's slower
Okay.
than exponential. That's the important part.
Okay.
Okay.
And it's also important to notice that this is a lambda corresponding to this sort of dimension x, right? But you have basically you have one lambda for each dimension. So you have another lambda for y and another lambda for z. So in a sense, I think people tend to think of these Lyapunov exponents also as the equivalent almost of the eigenvalues that we saw last time, in the sense that if they're negative, they sort of compress the space. If they're positive, they sort of stretch the space. And one point that I wanted to make is so it's not just, it's like three. These are basically, there are three different Lyapunov exponents here.
Because it's a three-dimensional system.
Yeah, so you have x, y, and z. So if we wanted to look at a system, for example, take the another mapping is called the Baker's map. And it's given by, this is a discrete system given by these types of equations. And if you go and read a little bit more about the Baker's map, where do they show the plot? Actually, if I start the Baker's map, it's sort of, it's a stretch, it's called the Baker's map because it's almost the transformation that governs it is almost what similar to what bakers do when they fold the space and they fold their batter. And so if you look at this map, this is sort of the type of system that you get when you plot x over y. And then let's stop it here. And here are the two Lyapunov exponents right here. 0.67328405. So I just wanted to see how much they change just over time if we let the time, we stop the time again. The last period, this is still 0.673, for example, for the first one, but the last sort of digits change. We let it run again. 0.672, we let it run again. .6730. So they vary as we plotted there too. They vary over time, but they keep constant within sort of a particular type of accuracy, certain accuracy.
Can you write down what the Baker's map, or is it up here?
Oh, I didn't see it.
Oh, the Baker's map.
What it actually is, the map?
It's right here. So these are the equations for it, and what it does is it basically, if the y constant is smaller than a certain, if the y variable is smaller than a certain constant, it stretches the space in a certain way. So this sort of part goes here, and then if the y, this part here goes. So it sort of maps the unit square into itself according to these mapping with different parameters. And it was just to show you guys sort of like a small small way where you see this constancy in the Lyapunov exponents. Okay. So so now to formally define chaos, I think chaos is, even the definition of chaos is very debated by different people, and different people have different definitions, but what is generally accepted is that chaos is an aperiodic, long-term behavior in a deterministic system, in the sense that the variables that we give, the parameters are fixed. There's no randomness that we ourselves give the system that exhibits sensitive dependency to initial conditions. So it's all about this type of aperiodic behavior which exhibits this very sensitive dependence to initial condition. And this is sort of the definition that most people agree on, and it's still quite hand-wavy and quite but this is sort of the characteristics of the systems that that people can agree on, that they can say then that exhibits chaos.
When you say sensitive dependence, do people always mean exponential divergence with time?
So generally it means, yes, that the Lyapunov exponents are positive.
But well, like what if it was growing like cubically? You had some divergence that grew cubically with time. Would that not be sensitive enough to chaos? So still like, an aperiodic system. Yeah, like lambda t all cubed instead of even lambda t.
I'm not sure. So the definition really doesn't say anything about the Lyapunov exponent. So if you have these Lyapunov exponents positive, so what we're trying to say here, if this is like this, then the system is chaotic.
What if it's not growing exponentially with time? So forget the Lyapunov exponent.
Right.
What if it's growing some way slower than exponentially? Is that I think those are typically not chaotic.
I actually don't know. It's if you have this aperiodic system with sensitivity to initial conditions, why would it be not chaotic? Like,
why is it? How do you define sensitivity to initial conditions? That's what it comes down to. You guys can see the definition is kind of fuzzy.
Right. So definition is very fuzzy, and this is basically you can read a little bit more in the book. But even in the book, I think there's this discussion, like in the chapter that I put online on like how we define these things and what exactly what Joel is saying. What does this sensitivity means? This is sort of the fuzzy definition that some people accept, some people don't accept, but it's accepted by most people.
Yeah, I think that if we could, I think that what's most accepted is this exponential form. So if it has exponential divergence, that's considered sensitive dependence on initial conditions, and therefore it's chaotic. But the aperiodic part is important. Like you were saying, you could have a system that's completely periodic, but its amplitude just grows. Well, I'm not sure. I'm trying to think about an example where you would get divergence like that and it's not chaotic.
So I think a Lyapunov exponent can be you can define, I forget the name, but it's not always relevant to delta between 2 points. You can define some characteristic that grows or shrinks, and the amount by which it grows or shrinks is the exponent.
Yeah.
It's a sort of open-ended definition. I don't remember the exact.
But are there examples of systems that
like something that periodically explodes with amplitude grows? You can
okay.
find a Lyapunov exponent that is positive.
But it's periodic.
Yeah,
so it's not chaotic.
I think so, yeah.
Okay. So then the aperiodicity aspect of that definition is very important.
It's very important.
I mean, if we had something that was periodic, we called it chaotic. We'd kind of be misusing language. So.
Cool. Let's take a 5-minute break now, and then after the break, we'll talk about the paper that you guys had to read and more examples of chaotic systems. But I actually wanted to clarify something about what the 1 over lambda was. So if we go back to our equation.
Give the sum function goes faster. Lambda t equals squared.
So if we look at this equation for the Lyapunov exponent, what we see is that, I wanted to go back a little bit to the 1 over lambda mentioned. We see that for t over 1 over lambda, we have lambda t is larger than 1. So people mention often 1 over lambda because this is when this number already becomes large. So it's larger than 1. So in the sense, a lot of the times 1 over lambda, so if you also look in the chapter of the book, sort of 1 over lambda is mentioned as, or multiples of 1 over lambda. So sort of this type of order of systems, it's mentioned when we can no longer predict where what happens to the system based on initial conditions. Because here, if t is much, much smaller, let's say, than 1 over lambda, then this can be sort of ignored. And that's when people use a lot of 1 over lambda when talking about, okay, anything that's larger than this as time goes by, this type of trying to make a prediction about the system breaks down. So that's when sort of this Lyapunov exponent comes a lot into play. Like, when does my attempt to make any prediction over what this divergence is breakdown. How fast does it break down? In terms of how much time does it need to pass before I can stop making predictions. So, for example, here, if lambda is really big, then time can be really small. However, if lambda is really small, then time just gets bigger. So, in that sense, these systems are different in terms of their Lyapunov exponents. Another point I wanted to make, and it's made in the book. It says this exponential divergence that we mentioned must stop when the separation is comparable to a certain measure called the diameter of the attractor that we're going to talk a little bit more about next time. And the trajectories obviously can't get any further apart than that. And this explains the level off or saturation of certain curves. So we're going to talk a little bit more about sort of diameters of these strange attractors next time. And another point I wanted to just think a little bit about concerning the definition of chaos. Think a little bit about this function. So this function, is deterministic, right? If we look at it, we can see that it shows exponential separation of nearby trajectories. So can we call this system chaotic? And in this system, actually, I think we talked about the system last time, and what happens is the system is that, yes, the trajectories diverge exponentially from each other, but they all go to infinity. So in that sense, infinity is a fixed point. So it's almost as if you have a fixed point here. So in that sense, the system here is not chaotic. You still go to this fixed point, even if it's aperiodic or because infinity here basically acts as an attracting fixed point, even though the trajectories separate exponentially over time. So these are just 3 quick notes that I wanted to make based on our conversation previously. So let's move on to the required reading that you guys had to the paper. Did you guys get a chance to read it? Do you wanna introduce the paper a little bit?
Yeah. Okay. Hi guys. My name is Sharon. I was one of the 3 assigned to do a reading presentation for today. And what I'm going to do is basically move through the paper super quickly in a general overview. So generally, the paper moves from defining the terms to talking about chaos in theory and practice, mentioning dynamical systems theory, and then kind of taking a meta view about the challenges that chaos theory poses to existing scientific paradigms. So it starts by defining it not super clearly. I was wondering why they didn't do that. Now it makes sense. And generally referring to chaos as a fundamental randomness generated within deterministic systems. And then it moves on to mention some of the key thinkers of the discipline, starting from how in the 18th century Pierre Laplace thought that given the position of and velocity of every particle in the universe, you could predict the future for the rest of time, which is this deterministic view that we just need to know all the information, and based on the rules that we know apply, we can know the future. But today, in the 20th century, things like the quantum mechanics introduce the Heisenberg uncertainty principle, which poses microscopic unpredictability, which kind of challenges that notion. But on a grander scale, chaos is what poses larger scale unpredictability. And then we learn about people like Landau, who thought that complicated motion along like several different kinds of combined oscillations made the flow impossible to predict, but he thought that the errors were bounded and predictable over the long term. And then Poincaré, I'm messing it up totally, came along and said that that's not true.
Good, I thought.
That's pretty good?
Yeah.
Okay.
I mean, I don't really speak French. I think it's like Poincaré.
Poincaré said that he introduced this idea of fortuitous phenomena, where a small change in the beginning condition could create like a huge change later on in time. For example, the idea of a stone rolling down a hill, you could poke it just a little bit in one direction, but 10 times as later it could be like completely on the other side of the hill. And so the idea is that any effect, no matter how small, could quickly reach macroscopic proportions. and that in real life, when we were measuring our surroundings, there are inherent uncertainties in the measurements, which will then be exponentially amplified and overwhelm our ability to make predictions. And then it moves into dynamical systems theory, introduces terms like what the state means and what a dynamic means. It also goes on to introduce attractor, which we've already talked about, which could be a fixed point or region that the system kind of settles down to or approaches. And then it talks about non-chaotic attractors, like fixed points, and this idea of toruses or tori, which I found really interesting. Attractors from in systems with quasi-periodic motion. So not non-quasi-periodic, but quasi-periodic, but inherently still deterministic. And not that other is not, but the oscillations remain regular and predictable. And the key, like, defining kind of intuitive principle is that particles that start near each other end near each other. And then they moved on to non-chaotic attractors, where particles that start near each other could end up completely divergent, as we've been learning, in a process of stretching and folding. And they're not simply noise amplifiers. They're noise amplifiers on a local scale, but the term the paper uses that qualitative behavior is independent of noise level. What that means is, if initial divergence was, it doesn't matter what scale the initial divergence was, in the long term it's unpredictable anyway. Or the divergence could be as large as if initial divergence was like 1/10 of the size, or something similar. And I think something that adds on to your question is the fact that they talked about in a system without dissipation, the orbits would relate to an energy surface. So what that kind of brings to mind is like I don't completely understand it, but what that made me think was like it made me imagine a large surface or plane where divergence could, you know, a plane is infinite on its sides, but constrained on certain axes. Right.
And it talks about this like stretching and bringing back together, right?
Mm-hmm. Stretching and folding, for sure.
Stretching and folding.
And then I just want to move quickly to the paradigm shift. So chaotic systems can be understood by breaking down, whereas a lot of like the modern science that we've been interacting with kind of had the hypothesis that if we break down the parts of a system and figure out what's going on in all these little deterministic laws, we could figure out everything. But chaos shows that complicated behavior can emerge out of even simple, non-simple interactions in a very non-linear way. So kind of like we can't understand even by breaking things down, and that physics cannot be complete. And I like the part where he said this is a mechanism that allows for free will within a world governed by deterministic laws. Thanks.
Thank you. Yeah, so what you mentioned last time is also one of the favorite things that I like about this paper, because everyone talks about chaos as this sort of limitation and prediction of systems, which is very true, but it's maybe not worthwhile to really look at it as a limitation and more maybe look at it more constructively in terms of providing all these natural systems with access to more diversity and more novelty in them. What do you guys think? So I'm basically referring to the last paragraphs of the paper. And also too, I don't know if you guys read one of the optional papers that looked at heart rhythms, but that's another point that they made in that paper, in the sense that a healthy heart has this variation in the way it beats, and it doesn't fall into these very like restricted type of periodic phenomena. It's actually, if you look at the heartbeats, it's very variable. And if you read that paper, they make a lot of they try to sort of think of it like, why would that happen? What does this? Why would a normal natural system be like that? And why does that actually break down when there are different type of heart diseases going on? So this sort of variability in the motions of the heart. So they also try to make this point of you know, or any type of biological evolution necessitating this variability. And you don't just see it, and you also see it in different populations. So for example, a lot of my PhD research is on looking at variability as a way to adapt to changing environments. And so chaos brings this sort of type of variability and novelty to the systems around us.
Just to add on to that too, I think it's really neat. I read some of the article about music, and it sort of had the same ideas that like the chaos of something could be celebrated as much as it is to be sort of detected, like even if it doesn't fit with scientific like structures that we can work with very easily, it definitely has like merit or benefit.
Talking about music, do you wanna show us the cool things that you're looking at?
Yeah. So, I can just start talking. So I just wanted to talk a little bit about chaos in music. There were 2 optional reading papers about it, and also I love this stuff, so I'm just going to talk about it. So there are like a lot of reasons why chaos has been incorporated into music, and like chaos and like random chants. And so one of the papers dealt with like different like mathematics that you can sort of apply to like a series of like they had like 4 notes, I guess, and they like, you know, like put those in a matrix, and then they would do different like a series of like operations on that matrix, and then it'd be like those 4 notes, and then they would flip them, and then they would split them, and then they would just like kind of do like different combinations, and just seeing kind of like what sounds they could make like using different mathematical patterns, I guess. And then kind of like broader ideas in general is people have wanted to sort of experiment with the idea of like, first of all, like, what is music anyway? Like, does it you know, I'll talk more about that in a minute. And the idea of just like making new sounds, I guess, like making like a piece of music that they will like perform and that will stand by itself, and that like since so much randomness has been thrown into it, like that same piece of music will never be heard again. Like they will never even be able to produce it again. So that's just like an interesting concept to some people.
Especially the idea that they can't produce it again.
Yeah.
Because if they try, no matter how hard they try, they'll eventually get hurt, right?
Yeah. So, and then a third idea is just like people want to like expand on already existing pieces. So if they have like a series of sounds or like a small piece of music, and they get kind of like with matrices, but wait.
I'm sorry.
That's okay.
I don't know how to stop this. Okay.
So if you like have like a sound bite or a song or something, and like what can you do to it to make it sound different and to make it sound better or to make it sound more interesting. So one of the things that the paper mentioned was artists who do like variations on a theme, and so they'll sort of be like a group of sounds, I guess, and they would manipulate it in some ways, such as like making some of the notes like longer or shorter or louder or quieter, just based on like either mathematics or just random chance, and see like how that sounds after a while. One thing that I think is really cool is some people do like phasing with the music as like a kind of variation, and so they'll have like kind of 2 tracks of one thing playing like starting the same, and then they'll speed one up by like a part of a second, and the sounds just like at first it sounds like a little bit weird, and then eventually it slips like so much out of sync that you can't tell what they're saying anymore, because they've done it with like words. Steve Reich? Yeah. Is one of those artists, and so he'll do it with like a short piano sequence of like 18 notes, and then they'll start playing those 18 notes, and then one of the people who's playing it will speed up, and then it like comes out of sync, and like it sounds just like totally chaotic, and then after a long enough time, 15 minutes or something, they'll slip back into sync at the end, and you're like, oh, I just heard like 18 different pieces of music you know, it's very interesting. So, and then what I was talking about with like some piece of music that you will never hear again, I was thinking specifically of John Cage, who is sort of like, what is music? Well, it's just sounds. And so, like, the piece 433, where it's 4 minutes and 33 seconds of people not playing instruments. And so, but the idea is that the piece isn't silence, the piece is whatever you're hearing in that room during those 4 minutes and 33 seconds. And so in a large concert hall, you probably won't ever hear the same thing twice. Or he has a piece called Water Walk, where he just like breaks things. Or like one of the sounds is like pouring water from a pitcher down a drain. And every time he does it, it sounds a little bit different, and that's just like, or like he would like change the order of things by like rolling dice and just seeing like, you know, what kind of random sounds can I make next, and is that music? So this video is, well, you'll see.
I mean, you can come in.
Okay, here we go. I don't actually remember the name of the person who did it, but it is on YouTube. And they made this like pendulum instrument, and each time, like one of those, I don't know if it's like hits its apex or passes the middle, it makes a different sound.
So they basically all start like same initial conditions.
Mm-hmm.
These pendulums are all, they're not connected to each other.
They're not
They
connected.
just have different lengths.
Yes.
So is this chaotic?
It's periodic, but over a long time.
And
So
it
they-
eventually converges to the fixed, what's the fixed point here? That the system converges to? The center, the zero, basically when all are not moving.
But even, what converges in like another, I don't know how many seconds. It goes back to the initial conditions. And like you get, you know, there's like a tiny amount of variation, so I guess that is an argument for, you know, if like one little thing is off, that system is never going to be exactly the same again.
Wow.
This is the same idea of the guys playing different rates, same piano notes over and over.
Yeah, so that phasing eventually will catch back up to itself, but then sometimes they even do more interesting things where like what, you know, when it's like halfway separated, they'll take that sound, split it, play that over again and phase that, you know, and kind of fractal that song out until it's just complete white noise, I guess. But it's very interesting. And occasionally it's like the picture that was in the chaos reading where, you know, they stretch it and then they chop it off and they take that and they stretch it and chop it off, and then like the 248th time or something, like you see like those little faces again.
Mm-hmm.
So it sounds like it's chaotic for you know, a long period of time, and then there'll be like this flash of like, oh, that's exactly what it sounded like at the beginning, and then it'll be gone again. That's what I thought to say about that.
I think part of the attraction that musicians and artists have to chaos is that in music and in other art forms, what you want is a balance between something that's predictable and something that's unpredictable and surprising. And on the extreme end of unpredictable is noise, and noise is not interesting. Something that's completely random is not inherently interesting to listen to. Something that's really predictable is not interesting to listen to either. And so there's this fun middle ground, and when you see like the Lorenz attractor, you have that same kind of wonder. You're like, oh, it's still generating variety, but at the same time it's predictable, and it's right in that comfort zone of surprise.
I think that's a great way to sum up what complex systems are. I mean, things that are completely random are just noise. They're boring. We don't care about them. We don't call them complex systems. Things that are very simple and periodic and repeatable that we can predict are not complex systems. The complexity is really right in the middle, and that's the interesting part. And that's the hard part to figure out.
One of the acronyms they use to teach complexity is BOR, which is between order and randomness.
So, I mean, like as you were mentioning, the randomness isn't very interesting. If you take a dice and you just throw it, it's going to be random. And random systems are actually very predictable. They're not predictable as in what's the next roll of the dice going to be, but you know that in the long run, if I'm flipping a coin, it's going to be 50-50. So in that sense, it's incredibly predictable. And so it's a very ordered system. Complexity and chaos is in this very interesting region where you get these things called like long-range correlations, which is like things. That's fractalness, or something that's fractal. They look the same at all these different scales, and that's people in music love that. When you have a song and you have a pattern that repeats itself on the scale of the song, but then you also repeat that pattern on the minute level and then on a 10-second level. That sounds very pleasing, and then those patterns can interact with each other, and sometimes they're all in sync, and you get certain noises, and sometimes they're not in sync, and you get other noises. So.
Do you guys have any more thoughts from the reading? We can play more music. Did you guys play? Did you go to the? Let's do that now. We can go to that science paper that I linked to, and we can listen to the variations that were in that paper. Were actually based. The pitches were based on the Lorenz attractor.
Do it. Make something happen. Yeah, try it out. And then the hard part is making it happen. Actually, sounds good. Interesting.
So, for example, track 1. This is just the map that they started with.
Could you briefly explain how these are generated?
Oh.
People haven't read the.
So basically, the way they're originated is, if you guys want to read more, is in this Dabby paper, so they have these different sequence of musical pitches. I'm not really sure. I don't really know what musical pitches are, but it's like the sound that.
Just a note.
The note, right? The note that you make, and so what they do is that. So, for example, they take this Bach or any other music, and they pair it with the X. So, with the X components of a Lorenz attractor. So, as you go on the attractor, they sort of map down to the X-axis, I think, and then sort of in this way, the X-axis becomes this sort of pitch axis of configuration. And then when you start with a different initial condition across the attractor, you sort of map back to the X-axis. You hit the X-axis in a different configuration, and so these sort of variations are that new configuration that appears.
So it would be like having the Lorenz attractor on top of a piano, and every time the little ball going around went in on top of one of the notes that did that note, right? Is that what that is? Each point on the x-axis is a different note?
Yes.
It's kind of like you had the Lorenz attractor play the melody the first time. So say you have X and the Lorenz attractor. Every time step, and you go through the melody. So there's like the melody is just a sequence of notes. So on the first time step, you take the first note, you play it.
And then you map it back to that. So you sort of you follow the curve, but then each time step you plot on the x-axis. You keep following that curve each time you plot on the x-axis based on where it takes you. And so now on the x-axis you have all these steps, 1, 2, 5, because you go back and forth, right? All these notes are then sort of not jumbled on the x-axis, but they are now on the x-axis. So then when you start with a different initial condition that takes you in a sort of differently, looking back on the x-axis, you can sort of play these notes in a different order, basically.
Does everybody understand that?
It's the same notes as the initial piece that you started
It's exactly
with,
the same notes, but
just rearranged based on the
rearranged.
mathematics of the Lorenz attractor.
Yes.
Okay.
I want to draw a picture because I think that'll make it clear. People can't see this. Just in case people don't understand. So you have okay, here's the notes on your hand. You have this Lorenz attractor and this crazy thing over here, right? And every single point, you can draw a line down. And so when it's at this point, it's going to be playing this note. And it follows here. And the next time point, let's say we grab this one. Okay, that maps down to this note. And then, what did I draw it doing? Well, it comes back over here now. So now it's going to go to this note. So we play 1, 3, 2 in this case.
And it's important to know that if you, it's all to do a little bit with how dense also I think this this attractor is, because every point basically this translates to a dense mapping on the r-axis.
Your picture suggests that it's sort of playing a piano, which is not quite accurate.
So notes in a.
It's not like, well, no, if you keep it that way.
These are just different frequent.
Right, it tends to suggest that that's like, you know, do, re, mi, fa, sol, la, ti. But it's more like if it were Mary had a little lamb. It's like, Mary had a little lamb. It's like the melody is spread out.
Oh, okay.
So you only have the notes of the
So you only take the notes from the melody.
Yeah. And they're in that order, in the order of the melody.
Okay. That's important. Thank you. Yeah.
Wait, so when does it decide when to just kind of like drop down and hit a note? Is that based on the rhythm of the original?
So
note?
I think it's based, I actually don't know what the rhythm is. I know, so every time point you map back to the x-axis, like every time point in the Lorenz system.
Is it constant time intervals?
Yeah.
I don't know.
Their system doesn't deal with rhythm. It just deals with rearranging pitches.
Okay,
Right.
yeah.
But you could imagine one that followed a particular rhythm.
Yeah.
Yeah.
Cool.
So let's say if we play, the initial track is this.
Sure, it has a constant
That's
time interval going on.
So this is the original, and then I'm going to play one variation that they had.
It's kind of more interesting, isn't it?
And now I think in the next one, they actually did a
Sounds like
mix
someone
of these
improvising.
variations.
Source of creativity.
Of the entire one. So if we listen to,
You can sort of hear it has a similar feeling to it for a little bit and then switches. That's like when it's switching to these different sides of the attractor.
and I don't know if you guys noticed, but for a while it was almost like repeating the same notes over and over again. So this is another one that I think is using, they're doing a mix of these variations, and I think it's also using more notes, more pitches. It's very soothing. You can just like listen to music.
It would be interesting to compare how this kind of relation would make if you would really have them in an order or random separate
Or like have some other mapping computer with not explaining all these different pitches.
So I really enjoy this.
And there are other examples. I'm gonna put more examples in an email to you guys this weekend. For example, I'm gonna link a little like YouTube video with the double pendulum. The double pendulum is also a very famous example of this chaotic system where if you start from the same initial conditions. Actually, I can play you the video of the double pendulum right now.
This is Steve Stroke, that's again. Now we're talking about Where here's the motion of the double pendulum.
You see what Steve's story looks like.
This is what he looked like 20 years ago.
Chaos.
Much more interesting thing to do is to start a solution in a full non-linear regime, let's say, like so.
So, can everybody see what this is? It's just two little rods connected with like a hinge there and a hinge there. In this case, they're the same length, about the
They
same
don't need
length.
to be different.
So this is something everybody here could build, and yet it's chaotic.
And eventually dancing has its way. Now, you'll notice that solution I started like this. I could start the solution with the same initial energy, like so. Do you think this one will be more or less interesting to watch?
These are basically different equations
Not just the energy
that govern these different systems.
Another thing we can show is what's known as sensitive dependence on initial conditions, and that can be seen by looking at two different solutions, or two different pendulum. They've actually made two nearly identical pendulum here. So let's start them the same, and let's see how long their motions stay together. Not very long.
Yeah.
So there are all these kinds of different fun systems that you guys can build yourselves or play with. And next time we're gonna talk more about this, the sort of the dimensions that we mentioned today in terms of the strange attractor, and more about fractals. Thanks. I'll see you guys next time.
While you guys are packing up, I want to say one other thing. You guys, if you take any calculus, should be able to show from this equation up here that not only do the positions grow exponentially, the difference in positions grow exponentially in time, but the difference in any derivative will grow exponentially in time. So the difference in the velocities will grow exponentially in time, the difference in the second derivatives will grow exponentially in time. So that's a characteristic of the kinetic system that's important. You can imagine a system where you have two different velocities and the distance between them grows in time, not exponentially, but the velocities are exactly the same. So think about that. Think about if you can show that mathematically.